So continuing what we learned yesterday, we're just going to see how far we get today. We should know that an odd degree function with a positive leading coefficient will always have the end behavior in quadrants 3 and 1. Here are the quadrants, 1, 2, 3, 4. So let's think about the most basic odd degree function, y equals x. Back in Algebra 1, we had equations that were y equals mx plus b, rise 1, run 1, plus 0. So yeah, it crosses at 0. It goes up 1 over 1, up 1 over 1. You could use that pattern backwards. What kind of graph do we have? We have this graph right here, okay? Now, where is that end behavior? It ends up here, upper right, and down here, bottom lower left, right? Quadrant 1 and quadrant 3, yay? And that's true for any odd degree function. Let's look at the next odd degree function. Let's say y equals x to the third. That's a cubic function, a parent graph of cubic functions. And you could even make a quick xy table to come up with the coordinates. If you did plug in a -2 into the x, you would have -2 to the third power, -2 times -2 times -2. That would be a -8. And then plug in a -1, -1 times -1 times -1 is -1. Plug in a 0, 0 times 0 times 0 is 0. Plug in a 1, 1 times 1 times 1 is 1, and 2 times 2 times 2 is 2. So if we graphed 0, 0, 1, 1, 1, -1, -1, and 2, 8 is going to be way up here off the graph, but you get the idea. It curves up and it curves down like that. So you get that snake-like curve. That's what this diagram shows right here. Y to the third, right? Down here and up there, quadrant 3 and quadrant 1. Just like this odd degree function, quadrant 3 and quadrant 1, okay? Now, what would happen if we were to put a negative in the leading coefficient right there or right there? All it does is it reflects over the x-axis. So this guy would reflect over the x-axis like this. This guy would reflect over the x-axis like that. Does that make sense? Good. Okay, so even degree functions with positive leading coefficients will always have that end behavior in quadrants 2 and 1, okay? Now, we already know the most basic even degree functions, a quadratic, the parent graph of a parabola, y equals x squared. And actually, yesterday, we graphed a bunch of different even degree functions. This is from yesterday. We graphed x squared, x to the fourth, x to the sixth, and we saw that all of them end up with that same end behavior in quadrant 1 up here and quadrant 2 up here. Now, what if you were to add other things, like instead of y equals x to the 10th, if you put like minus x to the 7th or plus x to the 3rd, add some other stuff, then something else may happen here. Like it might go up, down, but it's eventually still going to end up end behavior, both arrows pointing up. Okay? Okay. Do we understand that stuff? Yeah? Oh, you know what? We have a picture right here of any odd degree function. Yesterday we also did this odd degree functions, power of 1, power 3, power 5, power 7. Any odd degree function is down here and up there. Okay? You know what? Let's practice writing the end behavior. So on any of these odd degree functions, we did this yesterday, as x approaches negative infinity, what the heck does that mean? I know some of us are still lost and think like, what? I don't understand that. It's as simple as this. The x-axis is this guy. This is the x-axis. As you go this way, 1, 2, 3, 4, 5, and keep going, you're going to approach positive infinity. So over here is positive infinity on the x. Over here is negative infinity on the x. Up here is positive infinity on the f of x, which is really the y. And down here is negative infinity on the f of x, which is really the y. So all of these odd degree functions, as x approaches negative infinity, that just means look to the left. Where are the graphs at? Are they going to positive y value infinity or negative infinity on the y value? Negative. Okay, I hope everybody's paying attention. So as x approaches negative infinity, you're going to say f of x approaches negative infinity. And let's do the second one. As x approaches positive infinity, what does that mean? That means as you look to the right, because over here is positive infinity on the x. So as you look to the right, what are your y values? Are they approaching positive infinity or negative infinity? Obviously, they're up here. So that would be that your y values, your f of x values, approach positive infinity. Do we get that? Thank you. All right. Moving on. I want to ask you to talk to somebody about this, and I want to ask somebody for the answer right now. An even degree function with a positive leading coefficient will have its end behaviors where? Okay? Talk to somebody on a posit, and then I'll ask somebody right now. Go for it. Any volunteers?
Me.
Where does it end up? Okay, you lifted your arms up. Yeah, that's good. It ends up in quadrant 1 and quadrant 2. Think about this, guys. What's the easiest, most basic even degree function that we're really comfortable with? A parabola, right? Y equals x squared. And a parabola, the parent graph of parabola is y equals x squared. That has a vertex 0, 0, has a pattern 1, 1, 2, 4, 3, 9. So it's like that and like that. So yeah, the end behavior is up here, upper left and upper right. How would we describe that? You would say as x approaches negative infinity, f of x approaches positive infinity. And also as x approaches positive infinity, then your f of x approaches positive infinity, right? Now, any even degree function will have its end behavior up here and down and up here, okay? So what I did is I just typed in that even degree function right there, y equals x to the fourth, that's an even degree function, and I added a bunch of junk, right? Open up your Chromebooks and type that into Desmos right now. I'm going to pause it, and we'll unpause it once you guys graphed it. By the way, Desmos is pretty smart. If you forget to type in y equals, it'll still graph it, because it assumes that you're trying to graph a function. You will be able to use Desmos on the final exam. And on the next test, believe it or not. Yeah, it's amazing. So get comfortable with it. So check it out. If you graphed it correctly, you should have, and I just wanted to show you that you do end up with the same end behavior, both of them up, right? The leading coefficient's positive, so end behavior, it's both up. If the end behavior would have been negative, it would get reflected down, right? Since we're on this graph, I'd like to review some vocab. What would I call this point right here? What would I call that point right there? That is a relative max value, okay? Relative max. What does that mean? That means that it is a maximum value, but relative just to this little area, right? So again, like I mentioned before, if I say, let's stand up and see who's the tallest person here in the class, you could be the tallest one, but that's only relative to this class. If we go outside of the class and look at other classrooms, there's probably going to be more people that are taller than you, right? So that is a relative max only to this little area. But if we look at the whole graph, and I can't even see the whole graph right here, what is the absolute max? Well, there is no absolute max because it goes up forever, right? Okay. Is there a relative minimum? Yes? Okay. Is there an absolute minimum? Yes. Now, even though right here it got cut off because I didn't actually scroll down to see where it was at, but we could imagine that this graph comes down, 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 and then at some point it curves back up. So this guy right here would be the absolute minimum value, okay? Now, that's an absolute, but this guy right here is a relative minimum, right? Why? Because that is a minimum value, but it's only relative if you look at it zoomed in from here to here. Like, yeah, that's a minimum value for sure. But if you look at the whole thing, it's only relative to that piece. Because if you look at the whole thing, then this guy way down here is absolute maximum. Make sense? Okay, that's good. That's good. Oh, yeah. Might as well review it right now. I think on the final, it says which input value would give you, let's say, the absolute max. Or, absolute min. Which input value would give you the absolute min? So here's your x-axis, and those are input values. So what x value would give you your absolute min? -2 would give you that absolute min, right? If I said, like, más o menos, which input value would give you a relative maximum? Well, you would say maybe like 0.25 or maybe 1/4. That's how you would get there, right? Anyway, let's move on. All right, talk to a partner about this. An odd degree function with the negative leading coefficient will have its end behaviors where? Talk to a partner, go for it. Okay, guys, so we should know that an odd degree function, it has end behavior down here and up there, right? But if it has a leading coefficient that's negative, then what's it going to do to these end behaviors? It's going to flip them, right? It's going to flip them. Does that make sense? Yeah, so instead of like a cheerleader with pom-poms like this, if you have a leading coefficient that's negative, it's going to flip them and put them up here and down there. Maybe I should use the red.
Yeah, you're frozen.
So what would if we describe the end behavior, let's describe it as x. Now keep in mind, we're talking about the one that got reflected over the x-axis, so something like that. Okay, as x approaches negative infinity, that means as you look to the left, what are your f of x values doing? Are they going up or down? They're going up, so positive infinity. And as x approaches positive infinity, what does that mean? That means as you look at it to the right, are you going up or down? You're going down. Okay, I only have a couple of people responding right there. I hope you guys understand it. It's not a big deal on the final exam. There's only one question that has this stuff on it, but it's a big deal on next week's test, all right? So please understand it if you haven't, or please ask me right now. Stop me if you don't get it. Anyway, any odd degree function is going to have the end behavior up here in quadrant 2 and down here in quadrant 4, okay? With the a value being negative, right? So I'm going to type one in to Desmos. I want you guys to type it as well. Here it is. I typed in this guy. It's an odd degree function, and I put a bunch of stuff on there. Go for it. Type it into Desmos, and let's take a look at this graph. It's a long one. So if you type that in correctly, you're going to have this guy right here. Yay? Okay. Let me ask you this. How many real zeros does it have? What the heck are real zeros? Those are real answers. Remember, zeros are answers, solutions, x-intercepts, roots. They all mean the same thing. So right here, when I say how many real zeros does it have, it has 1, 2, 3. 3 real zeros, right? Now, here's an example of a fifth degree that doesn't have 5 directions. It's 1, 2, 3. So the degree, if you're looking at just the graph itself, you would say the degree must be at least 3, but it could be higher. It could be 5 like we have right here. Got it? Okay, let's go and practice that degree stuff. Check it out. I want to draw a parabola. Everybody pay attention right now. Not a parabola, a graph. And tell me what degree it must be. I want to start down. I want to start up here this time, like this. I want to go, What the heck? Kidding me? How many? What's the degree right there? 1, 2, 3, 4, 5, 6, 7, 8. Yep, that's right. How about this? The number out in front, I don't even know the function, but the number, the leading coefficient, is it positive or is it negative? Positive. Has to be positive, right? So yeah, this is the 8th degree, at least 8th degree. It could be 10, could be 12, but it has to be even and it has to be at least 8 because it does have 8 directions. 1, 2, 3, 4, 5, 6, 7, 8. It can't be 6. It can't be 4. It could be 8 or higher. And the leading coefficient has to be positive because the end behavior has both of them up here. Okay, let's try one more. Or a couple more. How about this one? If I say, What is the degree here? It at least has to be what? 7, right? Make sense? Cool. I don't know. That's getting kind of lame. Should I do more? Why not? One more. What if we have that's what the heck?
1, 2, 3, 4.
Let's just say 1, 2, 3. The degree must be at least 3. Could it be 5? Yes. Could it be 7? Yes. But it has to be at least 3. Okay, let's try something else. You know, this morning, I was messing with Desmos, and I wanted to produce a cubic polynomial, something with the power of 3, that would actually cross at 3 decent locations, right? 3 nice locations. So I'm like, I was guessing, I was just typing things into Desmos, and I wasn't able to get it. So I'm like, you know what? I'm just going to make my polynomial by making 3 binomials and then multiplying them out. Now, I'm not asking you to do this. I'm just explaining what I did this morning. So I took this x plus 2 and that 3x minus 1, and I distributed the x. I distributed the 2. I combined like terms. I got this red quadratic trinomial. And then I brought down the 2x plus 1. And then I distributed the 2x, and I got that blue trinomial. And then I distributed the 1 to all 3 terms, and I got that green trinomial, and I lined them up to combine like terms, and I got my cubic polynomial. Now, if I graph this, it's going to look nice. It's going to cross the x-axis 3 times, and it's going to be at some nice locations. Not like really nice, but one of them is really nice. What would those locations be? If this is the what the heck? Sorry. If this is the factored form of that, then how could I find my x-intercepts? I would split them and set them each equal to 0. So where would it cross the x-axis? -2. Where would it cross the x-axis? This is a little bit harder, but positive 1/3. If you set it equal to 0 and solve it, it'll be positive 1/3. And this guy right here, if you set it equal to 0, -1/2. Okay? So what I would like you to do is go to Desmos and type in y equals this polynomial, and you're going to see that it does cross the x-axis at -2, at positive 1/3, and at -1/2. So if you typed it in correctly, you're going to have this graph. And just like I mentioned, x-intercepts at -2, at -1/2, and at positive 1/3. Pretty cool, right? Now, let's say I gave you, check this out. I want to blow your mind right here. Let's say I gave you this cubic polynomial, and I asked you to factor it. Well, first of all, the only factoring methods that we used on 4 terms was factoring by grouping, and we know that right here factoring by grouping won't work. Like, yeah, you can pull out an x here, but over here you can't. You can pull out a 1, you're not going to get a common binomial. But what you could do, if I ask you to factor something like this, you could actually go to Desmos, type it in, and voila, you're going to get this graph. And once you know this graph, since you know that this is an answer, this answer is -2, right? And that answer actually gives you one of the factors of this original polynomial. What do I mean by that? Because if that answer, x equals -2, where did it come from? It came from the binomial that was set equal to 0 when you did zero product property. So if you add 2 and add 2, you're going to have your x plus 2 equaling 0, and that is the binomial that produced that answer, x equals -2. So in a sense, by knowing that nice answer, x equals -2, you know one of its factors. One of the factors is the binomial x plus 2. So if you're like, I don't know how to factor that, you could graph it, and if you see a nice answer, then you could actually come up with one of the factors from that answer. Pretty cool, right? Now, you're probably thinking, well, yeah, but that's just one of the factors. So, like, let's do something really basic. What is 21? What are the factors of 21? What times what is 21? 3 and 7, right? So if I say 21 divided by 7, am I going to have a remainder? No. 21 divided by 7 is 3, right? So if I were to take this guy and divide by one of its factors, it'll give me the other factor. Like 21 divided by 7 is 3. 7 and 3 are factors. Does that make sense? So if I know that this is one of the factors, I could actually do synthetic division, which would be plugging in this set equal to 0, which is technically the x-intercept, the answer, x equals -2. And then you have your list of coefficients, your 6, your 13, your 1, your -2. And then as you go down, you combine. 6 plus 0 is 6. As you go up, multiply -2 times 6, -12. As you go down, combine. 13 take away 12 is 1. As you go up, multiply. -2 times 1 is -2. As you go down, combine. 1 take away 2 is -1. As you go up, multiply. -2 times -1 is +2. And we already knew that the remainder is 0. As a matter of fact, if you don't get the remainder 0, you did something wrong, right? Kind of like 21 divided by 7. If you get a remainder, you did something wrong, right? So does that make sense? So based off of this nice answer, I came up with one of its factors, and then I did division, because if this is one of its factors, which it is, if you divide this by one of its factors, your remainder is going to be 0. Now, why would I want to do that? Because this guy right here is what we call a depressed polynomial. This is a bigger polynomial. This is a depressed polynomial. It's depressed because this lesson's going on so long. No, it's depressed because it's smaller. So what do I mean by that? This is actually the trinomial 6x squared plus 1x minus 1. That is a trinomial that I got from the 6, the 1, and the -1. And this is the other factor, x plus 2. Now, if I were to look at the graph again, and if I saw that these other answers, this guy right here and this guy right here, if I saw that they were crazy decimals, like let's say instead of 0.33333, if it was like 0.379824108, like I know that would be irrational, but because this is a nice decimal with a repeating 3, I know that that's a fraction. And I know that this guy is a -1/2. It's a nice fraction. I know that this is technically factorable further. So we're going to use the old factoring methods that we had before, where if your a value is 6, well, you're going to have to go a times c for your first step. 6 times 1, or 6 times -1 is -6. And then you make a list of the multiples, -1 times 6, -2 times 3. And then which pair of numbers combines together to give you the middle value b, which is 1. That'd be the -2 and the 3. And what do we do from there? You write your factor form answer format with the ax as the first part of your binomial on both. And right here, your ax is 6x. And what do we do with those blank spots? You put in the pair of numbers from step 2 right there and right there. So you're going to have a -2 right there and a +3 right there. And the fourth magical step is to divide each binomial by whatever you can. So right here, you could divide by what? 2. So what do we get? And over here, you could divide by what? And get what? 2x plus 1. Okay. So, ladies and gentlemen, we have factored this quadratic trinomial to these two binomials, and we still had this original factored, or factor of it, knowing that answer x equaling -2. So let's bring that down. And this right here is the completely factored form of the original. I don't know about you guys. I think that's amazing, right? Where we could take a huge, crazy polynomial that we have no idea how to factor. We could graph it and get those answers and work backwards to get the factored form, okay? As a matter of fact, you could have worked backwards just with the answer being negative x equaling -1/2 and x equaling +1/3, because if x is -1/2, where did it come from? It came from the binomial that was set equal to 0 that gives you this answer. So you would say times 2 times 2, you came from 2x equaling -1, and then you could go +1 plus 1, and you'd have the 2x plus 1 equaling 0. And then the other one, the x equaling 1/3, where did that come from? It came from multiplying by 3, having 3x equaling 1, and then subtracting 1, setting it equal to 0. So you'd have the 3x minus 1 that's set equal to 0, and technically that's even faster. You have that binomial 2x plus 1, that binomial 3x minus 1 with the original binomial x plus 2. X plus 2, 3x minus 1, 2x plus 1. Is that too much? That's too much. I'm sorry. Okay. But I want you guys to try it. Go ahead and write that down. Type it in Desmos. Type it in Desmos and graph it. And what are you going to do? If you have a nice answer, you're going to use that nice answer to depress the polynomial. And of course, you want the remainder 0, but you're going to depress the polynomial. That way it becomes from a power of 3 to a power of 2, and we should be able to factor the quadratic trinomial from there. Or you could just graph it, get your answers, and work backwards from your answers to the original. So you guys are telling me that the one nice answer is -2. If you graph it, yeah, you're going to see that it is at -2. And this guy right here, what is that guy when you click on it? I don't have it live on my computer right now. So what is that? It's 1/3. So x equals 1/3. And how about this guy right here? Is that 1.5? Okay, so I could write 1.5 as 3 divided by 2. So x equals 3/2. Now, you could use that answer of -2, and think about where that answer came from. It came from the binomial x plus 2 being set equal to 0. That means that x plus 2 is one of the factors. And if you wanted the other factors, you could use synthetic division and actually divide and have your list of constants, the 6, the 1, the -19, and the 6. And as you go down, combine 6 plus 0 is 6. As you go up, multiply -12. As you go down, combine, it's -11. As you go up, multiply +22. As you go down, combine, that's 3. As you go up, multiply, that's -6. And we're happy because that remainder is 0. And we know that if you divide a polynomial by one of its factors, you should get 0. This is your remaining quadratic trinomial, which would be 6x squared minus 11x plus the constant 3. And you have this other original factor that we got from that nice, beautiful answer. And you could continue factoring with that long process, right? Or you could just use the answers themselves to factor that as well. Because, well, we already know that the answer x minus 2 came from x plus 2 being set equal to 0. But where did the x equals 1/3 come from? X equals 1/3 came from what binomial set equal to 0? Times 3 times 3, that's a 3x equaling 1, because the 3's cancel. And then you would subtract 1, so you'd have 3x minus 1 equaling 0. So there's one of the factors, okay? And then the other one, same deal, you have x equaling 3/2. So you could multiply both sides by 2, and you'll have 2x equaling 3. And then you could subtract 3 on both, and you'll have 2x minus 3 equaling 0, and that is another of the factors. So if I asked you to completely factor the cubic polynomial that we have up there, and you found out that this was x plus 2 that was set equal to 0, you found out that this was 3x minus 1 set equal to 0, that this answer was 2x minus 3 set equal to 0, then your factored form is the binomial x plus 2, the binomial 3x minus 1, and the binomial 2x minus 3. This is your completely factored form of the original, okay? If you were to multiply this times that, and so on, and then combine like terms, and then get a quadratic trinomial, then distribute and combine like terms, it will give you that original cubic polynomial. All right, guys. You guys look tired. It's Friday. There's an assignment on Google Classroom. It's a practice quiz, but it's just a homework assignment. There is no actual quiz on Monday, okay? We're just going to move on to the next section, which is technically this section. We already covered it, right? But we're going to have a test on all of this stuff next Friday.